Hi everyone, welcome to the new session of 5G non-standalone training. Would be the session number 5 for the non-standalone series. Actually, today's session will be the second session of the 5G non-standalone planning. We are going to cover two parts, which is related to NR operating bands, and we'll have a very interesting topics under this part. And then we'll move through the SSP planning, and this is also covering in details about SSP for many things, which we are going to check in the next slide. So let's move forward. So as you can see here, for example, today we are going to cover these three parts, which is related to the operating band. Under the operating band, we are going to cover very important topics related to that. What is the meaning of supplementary carrier downlink and uplink, and what is the use cases of those? How to you can utilize it or use it in case if you have it in the network. Second part about one concept called overlapping band, and this overlapping bands, there is one feature which is can work with the overlapping bands called MFPI, multi-frequency band indicator. Then we're speaking about the NDC combination, carrier combination in general, how you can verify it from the ULO. Then the second part, it was about the NRFCN. We'll just compare quick comparison between 4G and 5G, and we'll show this new concept called GSCN, how to make the calculation for the SSP, for example, center frequency. Then the last part, it will be the impact of SSP in different speed, search time, and the RSRB RSC. So this will be the second session, and the previous section already covered this slot format in detail. So let's move forward. So actually, the first part just a theoretical recapping our theoretical knowledge about what we have in the 5G. As you know, that the 5G in general now can operate like for the bandwidth up to 20x higher bandwidth compared to the 4G, right? Because of now you can supporting, for example, FR1 up to mid band, which is, for example, C band, let's say 3.7 band and even higher. And you have the second range, which is FR2, which is supporting up to 400 megahertz as a bandwidth. The FR1 supporting up to 100 megahertz as a bandwidth. As you know, in 4G, we already supporting only maximum bandwidth as for single carrier as 20 megahertz. So this first part. So actually, what is the differences now if you are using low band or mid band or high band in the 4G? So, for example, low band will help you in the coverage point of view. For example, you will have a wider coverage and better coverage. For example, if you're using 900, 1800, you can get a better coverage compared, for example, to 3.7 or even higher. So the lower the band, the better the coverage. As you can see here, the low band, you have higher coverage, going mid band, moderated coverage. Then you will have high band, the coverage now is shrinking a lot. And that's why, for example, mid wave or high bands, maybe it will be more used for the small cells and so on. And the second part, it's about that part, it's opposite way around from the capacity. The low band will offer a less bandwidth, so you will have a less capacity. And the more you go up, there will be the higher capacity, and the highest for sure it will be milliwave because it will be up to 400 megahertz. And for the latency, the ultra low latency now will be supporting more about the high bands, and ultra low latency related to many features. For example, the many slots in the future deployment, or even the subcarrier spacing. As you know, the more increasing the subcarrier spacing, the lower the latency. This is also one of the advantage. Even for the slot format, also can provide some improvement in general in the latency. So this is also one of the things we would like to recap. One of the things we would like also to share it with you. For example, assume that now operators in general, what kind of the consideration they would like to do you usually check whenever they are going to have a new band or trying to have an auction or like trying to purchase a new band? So, for example, the first part it's about the coverage and capacity needs, right? This is based on needs, and as we discussed there. For example, if you're looking for coverage and this kind of scenario or capacity, so you look into that part. Or capacity also it's related to the bandwidth. What is the available maximum bandwidth per band, for example? So this is also one of the things. And the other two factors, which is very important, it's because it's more related to the capability of the devices. For example, how many devices compared from one band to another. For example, assuming N77 and N78, what is the maximum combination of NDC with other bands for 4G or and within the 5G supporting by this band? This also should be considered as well, because this can impact your users as well, right? You can have less users if you have less NDC band combination, as an example. Same for the carrier aggregation. This can support in the future if you have NR more bands supporting NR by carrier aggregation combination. This also can support your network to have a better performance, especially when you are deploying more carriers in the NR. And the next part is about the ecosystem, whether the new band will serve the 5G ecosystem or not, and also the future needs about the ecosystem and the future needs about the application or whatever you are going to deploy in the near future for the 5G. So this is the main consideration about the usually that operator is going to check. And also there is more other points, but let's just try to summarize it to the things which is more related to our technical work. So moving forward now, let's move to the next part. It's about related to the important topics, which is SQL, SDL, and so on. Before jumping to the important concept, I would like just to take with you just quick recap of how to verify or how to check the current bandwidth or information about your bandwidth for non-standalone whenever you need, for example, to compare one side to another or between different operators and so on, how you can do that from the DT logs. First, the table on the left here is just going a sample from all the supporting band for NR. As you know, that is, as we speak in the previous session for the PNR slot. We have this different duplex mode FDD TDD, and we have even half duplex FDD. And also there is another duplex called SQL and SDL, supplementary uplink and downlink, and this will be explaining details. And I will attach one table in video description which is covering all the bands of the NR. And here it is just supporting band, for example, per SCS, just to give you for information. This is only for FR1. So in the figure on the right here, as we discussed before in the explicit session, as you can see here, this is how you can check the current NR band, for example, and band is supported. Under the RSC configuration message during the SGNB addition, you will find under this message, I'll search for SP cell, secondary primary cell configuration. Under that part, you'll find frequency information downlink. Under this, you'll find the SSB location or frequency and the frequency band indicator, which is N78 here, for example, and here is the bandwidth, and here is our carrier spacing. So this is how you can verify. Now let's move to this concept in the bottom left here, which is very, very important to understand it. This can benefit in case you are doing analysis or even some network insights. So let's move forward. So the first part I would like to discuss with you, just to quickly recap that the NDC band combination or carrier aggregation combination. First, how you can read it from the 3GPP tables, and second, how you can read it also from the capability logs. For example, here in this 3GPP table, as you can see here, this one is showing the NDC band combination. For example, here you have DC dual connectivity, 1A, 3A, and N3A. And this table is representing whenever you have 3 bands supported by the device. And in the 3GPP, you will find also 2 bands, 4 bands, 5 bands, even up to 6 bands, but I just give samples from 3 and 4. So example, this is for NDC configuration for downlink. So you have 1A, 3A. This means you have 2 carriers for 4G, band 1 and band 3. Then you have N3. So you have N3 as well, supporting by the 5G as well. So here you have 3 carriers. And here for the 4 carriers, for the 4 carriers part, you have 1A, 3A, and this means you have 2 carriers for 4G, and then you have N3 and N41, which is mean you have 2 carriers for NR. So this is how you can read it, as you can see here. If you don't have anything like, for example, N, this means for 5G. If it's, and it will be always separated by dash. If it's like within the NR, for example, this is within the, and underscore if it's between 4G and 5G. This is how you can read the band combination from the 3GPP documents. Now in the right figure here, as you can see here, this is from the U capability logs. For example, I open this message, which is called UEMRDC capability NR. This is during 5G non-standalone. After this message, you'll find this kind of NR parameters under tariff parameters MRDC. Then you'll find the band combinations being supported here. Usually you find it like this, band UTRAN, for example, here is showing as 1. This is band 1, first one. A means it's only single carrier. This is the class like telling you, for example, how many carriers you have, 1, 2, contiguous, non-contiguous, and so on. I have one video in details about that part also. You can refer to this video. Then here showing this is the first band, which is the anchor, band 1. Then you have a second carrier for the 4G, which is band 3. And also this is again showing as A. This means it's only one carrier. So far you have 2 carriers. Then here you have additional carriers, which is 41. Band 41, but this time it's C. C means it's 2 carriers. So in this case, you have 4 carriers in 4G. And if you're going to 5G, you have only 1 carrier, which is N77A. So now you have as a total 4 LTE carrier components plus 1 NR carrier component. So this particular device supporting up to 5 carrier component, 1 for 4G and 1 for NR. And this is just showing the exact same format as you. This is important to understand, but the most important point, try to look into these tables, because sometimes you just need to know for your reference. For example, If you have different frequencies in the network, you need to confirm which one is being supported by 3GPP as a band combination. So let's move forward for the next part. So the second part here, actually, we are going to discuss a very important concept. It's about something called operating bands and MFPI feature. What it means by operating band. In the normal case scenario, there is a one-to-one relationship between the frequency spectrum or the spectrum. For example, if you have, let's assume your network, you have a band from 4100 till 4200. So this means it's directly means this is N77. So this is whenever this is a normal case scenario. Most of the scenarios like this, you have one-to-one relationship between the frequency spectrum and the frequency band. So one spectrum, it will be having only one NR. But in some cases, as showing here, for example, N77 starting from 3300 till 3800, it's overlapping with N78 within the same band, right? Same for N2 from 1850 till 1910, overlapping with N25. So this means whenever you have, for example, assume current network you have 3200 to 3400, this means you can even configure this particular frequency spectrum as N77 or N78. So what is the trick or what is the way around here? Actually, the main challenge is here that let's think about from two different perspectives. The first one, that some devices might support N77, not supporting N78, and the opposite way around. Some, for example, as showing in the bottom down here, if you look, this is the NDC supporting maximum band combination. For example, interband two bands, you'll find that N77 supporting more band combination compared to N78. This is supporting up to 96 different band combination and supporting up to 88 different band combination. So in this case, sometimes you'll find that you might having a less speed or even cannot access because you have a less combination if you configure yourself as N78. So now it's two different things. First, carry aggregation, and also it can impact the initial access. So how you can solve this situation? Actually, there is a feature called MFPI, which stands for multi-frequency band indicator. And this feature works in terms of accessibility point of view, or even during the carry aggregation or NDC. So how this feature is working. Assume now you have a device, which is this device, particular device, only supporting N78 and this device only supporting N77. So in this case, you need to configure both frequencies to within the site using this feature. This feature can configure both frequencies, and whenever the user is initial access, if you speak about the standalone here as an example, or 4G, same also concept, within the SIB1, the will deliver the system information block type 1 with both frequency band. For example, assume that here we have this scenario in N2 and N25. We'll find that under the SIB1 message, it's delivering both N25 and N2. So if you have one device not supporting N25, he will just access to N2. And if he's not supporting N2, he will adjust access to N25. And he's supporting both of them, he will take the one with highest priority because this feature also defines a priority between both of them. So this is in case of initial access. The same information can be delivered in the 5G non-standalone under this NDC X2 setup response. Whenever you have NDC X2 setup response, you will find that this also information being delivered for the NR frequency. This is actually how it can be solved. And in case, for example, you have a carry aggregation combination, for example, let's say N77 and N78, still the user will be able also to read, for example, let's assume that you have two frequency bands in your network, for example, one for N77 and one for N78, and you're configuring this one from you have this from 3500 to 3.6 or 3.3 to 3.4. So the MFPI will let the user read both of them. For example, let's assume both of them as N77. So if the user of the carry aggregation only supporting N77 plus N77, in this case, the users can enjoy the services of the carry aggregation or even for the initial access. This is a very important feature. I didn't try it in 5G yet, but I have tried in 4G, and I have observed a very good increase in the carry aggregation users. And when we tried this feature, it was between band 38 and band 41. This is in 4G. So this is just an example for your reference. So now let's move to the last concept about the NR operating band, which is related to supplementary downlink and supplementary uplink. See what we can get from that spot. Okay. Now for the supplementary downlink and supplementary uplink. What means by this? This means that some particular frequencies are shown in the bottom right here. For example, I give a sample from N8 and N29. I will just also show you the complete combination which you have it in the from 3GPP. I will show you the complete band list. But for example, assuming this part, this means this frequency only NA80 can only be used for uplink. And this one can be used only for downlink. For example, this one overlapping with one of the 1800 band, it's okay. But this one, it's just for the SDL. For SDL supplementary downlink, can be used for carrier aggregation only. For example, can be configured if the user, the operator, for example, purchase one of these carriers, he can configure it to be used only as a carrier aggregation. So it can be used as a capacity wise to offload the any of the existing sites through configuring this carrier as a carrier aggregation. So this is a use case of the SDL. You find I have seen some networks already being used that in 4G, not yet in 5G, but I have seen some network having some carriers which is only supporting SDL downlink. So this can be used only for carrier aggregation, no any other use cases. For the SUL, actually, this is very, very useful, especially for the current scenario for the as you know that NR, especially if you're speaking about the C-band, if you look into this figure in the left here, this is showing the coverage, or the red one, this is for band N78. So you can see that downlink coverage can reach from till the edge, while the uplink coverage is only reaching till this black circle, as you can see here. This is the maximum. So you have a limitation in the uplink coverage. So in this case, even your downlink coverage is extending till here, but you cannot enjoy this particular area because of the limitation doubling, because as you know, all the feedbacks need the uplink coverage. So in this case, for example, if you have existing SUL network or carriers from the 4G can be used as SUL, this case you can configure this carrier as SUL, so it can be working as a supplementary for this particular N78. So the uplink will be through the SUL and downlink will be through the N78. So in this case, you extend the coverage, as for example showing in the right figure here. The right figure here is showing that example for C-band. I have a C-band here, and I have the 4G. I have used the uplink of the 4G to be utilized as NR for 1800 band as NR uplink. So in this case, the coverage before was being limited till here only. Now I can extend it by this far because of the supported of the uplink here. So I can extend it up to this particular range whenever I'm using, and this is called the feature called uplink downlink decoupling. I believe you might be aware about it. So now let me quickly show you the complete band combination which you have it. Also the band combination and what kind of bands currently support ZL and ZL from the 3GPP table. Okay, as you can see in this table, this is from the 3GPP. As you can see here, you have this is a supporting uplink band and this is downlink band, and you have here double smooth. So if I filter here, I can just filter on SDL and UZL, for example, those two. You'll find that this is all the current combination which you have it supporting either uplink or downlink. For example, only these three carriers supporting is downlink, and all of these carriers supporting uplink. Whenever you see this 8 comment or a comment, for example, in one of these carriers, this means you need to look into nodes. For example, here giving a node 8, so this means N95 is mentioning that this is only applicable in China. So this is not applicable in any other country. So this is an example. The second part, which is very, very important as well, from 3GPP table as well. If you look into this part, this is the current combination. For example, assume that you have N78. So and you have other 4G carriers which you would like to use it as a supplementary uplink for the 5G. So in this case, you need to look in 3GPP table to confirm which band is being supported by which band. For example, this one, the combination between N78 and N80. N80 is for 1800. And for example, this is between N78 and N81. N81, for example, this is for 900 band or 800 band, and the same for N82, and so on. So this is also one of the important points, and I will attach this sheet also in the video description. So now let's move back to our video to continue with the remaining part about this SSB. So now let's me first recap one very important concept and differences, nuances between 4G and 5G before jumping into the details about the NRFCN or center frequency or SSB impact in general. So as you can remember, if you remember, in the 4G, you have assume this is your bandwidth. You have this is a complete bandwidth. In the 4G, that this is a center frequency of the channel bandwidth. And in 4G, actually, the center frequency of channel bandwidth and the broadcast channel or the SSB, was using this exact same center frequency, and the SSP and BSSS, SSS, and so on, synchronization signal and broadcast channels, was being fixed in the 4G. You cannot, it's not flexible. It's just in one particular location. So in this case, you are only configuring one center frequency per. The 5G concept now is completely different. For example, first of all, you have the center frequency one, which is related to the channel bandwidth. For example, this is the center frequency of the complete bandwidth. And you have another center frequency of the SSP or the broadcast channels or the synchronized signals. And this is actually the main idea, that in 4G, first of all, the SSP is being flexible. And why it's being flexible for many different reasons. But the most important reason is about the bandwidth part. In case you would like to have a different bandwidth part in your network, so you will need to have a different center frequencies of the synchronization signals. So for example, here in this case, you have in this particular cell, you need to define two different center frequencies. One for the channel bandwidth and one for the SSP block or the broadcast and SSP BSSS synchronization signal. All the mobility is mainly happening through the SSP. So this is also having more other considerations we need to check. So this is just a summary. And the second important part about the 5G, that the location of the SSP or the synchronization signals are broadcast is flexible. You can define it anywhere. For example, at the end of the band. For example, you can even move it to the center of the band, or you can even configure it at the start of the band. But just as a summary, you would like to configure two different center frequencies. So now let's move to the details about that part. We covered in more details about, in general, how to calculate and what kind of differences we have in 5G. So actually here for that part, I would just like to explain for you how we can calculate the center frequency in general in the 5G. And as I mentioned, we have two different center frequencies, one for the SSP as shown in this figure. Here, this is the frequency, and one center frequency for the complete channel bandwidth here. And there is two different methods to configure the center frequency of the SSP. It can be even through something called GSCN, which is standard for Global Synchronization Channel Number. And this is actually, it's being introduced, we call it synchronization raster in general. This is being introduced in the 5G because, as you know, the 5G will having a huge bandwidth. So, and every time the user is trying to access, he need to blindly scan until he found the location of the SSP. So, for example, in 4G, it was using fixed, which is 100 kilohertz. The user is searching every 1 kilohertz until he found the location of the synchronization signal broadcast. But in same concept 5G, but as you know, the 5G bandwidth is very big, so the user might take a very long time until he find the SSP location. That's why they have this kind of GSCN. As you can see, the main differences between the NRFCN or the channel raster and synchronization raster, that this is how the user is being scanned. Actually, synchronization raster having has a relatively low resolution. For example, instead of moving each 100 kilohertz, the users can move or make the scan each 1.2 megahertz. And this means the SSP locations at fixed location. For example, each band ranges will having a different, as you can see, scanning span or frequency span. For example, here it's moving every 1.2 megahertz or even 1.44 megahertz or even 70.2.7 megahertz. So actually, this is the main idea about the why the 5G introduced GSC in general. And non-standalone, you can either configure the SSP center frequency using GSCN or using this NRFCN, which is both of them having a different frequency, but they are equivalent to each other. But the recommendation in general to start directly with GSCN, because GSCN can work with both non-standalone and standalone. So in case if you're moving now, you're having a non-standalone and you started for configuring this one using the old way around, which is the NRFCN. In this case, once you are moving to standalone network, you need to again to change the configuration from NRFCN to GSCN. So just to save time, just from the beginning, make it based on GSCN. So now let's explain how we can make the calculation about the SSP, and I have a detailed video about SSP. You can look into this video in case you would like to find more details about it. So actually, as you can see here, we have two different methods to calculate the center frequency in general, especially for the SSP. The first one on the left here, which is NRFCN or RFCN calculation, and this is a straightforward and very, very easy one. For example, this is the formula NRFCN. You have the first one, the offset, and then the frequency range, and the frequency offset, and delta F global. This is the the formula. So if, for example, assume now you have your frequency range is falling between this, you have three ranges, falling between 0 to 3000. Assume now your center frequency, proposed center frequency, which is this one, F reference or F ref, this one is 2530. So this means your global will be 5. This means your offset here with this one, frequency offset, and this one will be both of them with 0. So if you just apply the formula here, this will give you the NRFCN, which is being calculated. This will be your NRFCN, which is being used to configure for the SSB. This is in case if you would like, for example, to use NRFCN method. For this one, it's kind of complicated, but still we'll go through the Excel file, Excel tool, which you have it for the planning point of view. Also, there is different tools and links in the internet. I also drop some of them in the video description. You can look into it in case you would like to calculate directly. So also the same concept for the GSCN calculation. It's having 3 different formulas because each range, frequency range, will have a different formula. As you can see here, there is something called N factor and M factor. And actually N and M factor was being introduced to, especially for the first frequency range, just to ensure there is the alignment between the subcarrier alignment between the main channel, the channel bandwidth in general, and the central frequency on channel bandwidth, and the SSB block. So it should be usually multiple of 100 kilohertz. The 100 kilohertz should be multiplied by that part just to make the alignment. So for example, if your frequency range is falling between 0 to 3000, you need to use this formula. As you can see here, the highlighted one, which is N multiplied by 1 2 megahertz plus M multiplied by 50 kilohertz. And this is the GSCN formula. GSCN formula, this is in case if you would like to calculate the frequency as a frequency, megahertz. And if you'd like to calculate the GSCN, it's equal 3 multiplied by N plus M minus 3 divided by 2. So this is a formula. So N, I'm showing you now the exact calculation about that part. M, first of all, it's having 3 ranges, 1, 3, 5. And again, this is just to make the alignment. Usually the one we are mostly using is 3, which is achieving our requirement to be aligned with the low band or the 4G, which was using 100 kilohertz. So usually 3. So let me take you through an example in the Excel file just to try to explain more how you can do the calculation manually. But again, not really very important because we have many tools about that part. Just understand that for the GSCN, it's having low resolution because it's increasing the frequency search or frequency span. The user, for example, for this particular band, it's moving searching for SSB 1.2 megahertz, while for this one, searching every 1.44 megahertz. So let me take you through an Excel file to show how we can calculate the GSCN and also for the NRFCN. So in this Excel, as you can see here for the SSB calculator, here it is for sub 5 gigahertz. For example, here there is showing inputs. This is you need to give your, for example, the NRFCN if you would like to calculate to frequency, or the opposite way around if you have already the center frequency defined and you'd like to get your NRFCN, if in case you are going to use NRFCN. So in case you would like to get it to configure it in your system. So in this case, for example, here this formula is exactly applying the formula which is being discussed, which is this one, NRFCN equal N reference plus this one minus this one divided by the delta F global, which is being shown here. So we're just giving F formula. For example, if the frequency range less than 3000, so we need to consider this as, for example, as 5. This one as delta F global as 5. Otherwise, it will be, and the other will be 0. And if it's, for example, this one, so we need to consider as 15 and so on. For example, here if it's between 3000 till 24250. So in this case, you would like to consider this one as delta F global as 15. So in this example, for example, assume now you have your center frequency, you have a frequency range starting from 3000 megahertz till 3.8 megahertz. So this center frequency would be, for example, for this channel bandwidth, you just need this one plus this one divided by 2. So it will be, to convert it to kilohertz, it will be this particular range. And a case also from 3400 to 3500. So this will be center frequency as example. Talk about the channel bandwidth. So this can be any other value depending on your configuration. So if I change this one to 3000, then this one, it will give you the RFCN and RFCN which you need to configure in your network. The same concept for the SSB frequency range. For the SSB frequency range, also here, in case you would like to calculate even the GSN or here, if you'd like to calculate, for example, the GSN, this is will be using the formula, applying the same formula which here in the Excel file. For this part, we just need you to give the inputs manually here, so to give you the formula as well. So let me take you through a detailed part for the SSP definition of frequencies, one by one. For example, just to explain more what it means by n factor and m factor. Assume now here our formula, right? For here I'm using for the N78 band, which is starting, for example, from 3000. Okay, this is the frequency. So this is the start of the band, which is 3000. Assume your band is starting from 3000 till, for example, end of this one till the maximum. Because as you know that the in general the frequency range, this one starting from 3000 till 24250. So the first n will be starting from the n variable. Will start from 0, right? From 3000 till the end, till you reach into the 24250, as you go down here, 24250, this one. And here, as you know, that the frequency location or SSB location will be moving each 1.4 megahertz. For example, here you can see this is adding up 1.4 megahertz. This is the SSB frequency location. Then again, it will add another 1.4 megahertz, and again 1.44 megahertz. So it's in the fixed location, but the user scan each 1.44. So this is how you can understand the frequency range as well. For the GSN in general, this is a very easy formula. It's just, as you can see, GSN equals 7499 plus n. So you just this one, you make this one 7499, this fixed value plus the n value. N value is here is 0. For example, your GSN will be this part, and the same for this area, which is, for example, you are making 7499, which is here, plus this 19. So this is how you can calculate it. So this is straightforward. So for the more complicated, it's about the, for example, assuming that you have 2.6 band here, for example. And as here, you know that this is again starting from 0, right? The frequency range starting from 0 till 3000. So the first one, for example, here is starting from 1, and the end will be till 3000 almost. But this time, this moving each 1.22 megahertz, right? As you can see, this is 1200 kilohertz divided by 1000. So it should move each 1.22 megahertz. So here, actually, as you can see, now if you would like to calculate the frequency, you need to make what? You need to multiply the n, multiply by 1200, then you will make it m multiplied by 50. M multiplied by 50. So this is the m. Here, m, I assume 3 values for m, m1, m2, m3, and m5. So you're calculating for two different the m, and also the same here. Then the last one would be about the GSN, how to calculate the GSN. GSN simple way around, just the 3 divided multiplied by n. So this one multiplied 3 multiplied by n, which is 2, for example, here. Then plus m. M here it can be 1, 2, or 3, 1, 3, or 5. Then m minus 3 divided by 2. This is how you calculate your GSN. And then again, usually we use our M3. So I assume that your center frequency is here. So this will be your, for example, this one will be your GSN value, which you need to configure in the system. So this is how you can do the calculation. Now let's jump to the last part from the SSP, the impact of SSP different location and performance. And this is a very, very good one and very important one. Okay, the last part here, I'd like to take you through it. Actually, the SSP location in general can have a different impact in the performance. For example, as you can see here in the left figure here, the SSB you can configure it in the center and the start of the band, as you mentioned before, right? So what is the differences? Like if you make it in the center frequency to be aligned, for example, with the 4G, or to make it in the start, right? So for example, the first part is about the less search time. The user need to search every time blindly decoding the SSB until he found the SSB location. So in case you define it in the center of the band, the users will, if this assuming this is the center, the user will need to keep scanning, right, until he reach into the SSB. While if it's in the beginning of the band, the user will quickly find the SSB and he can quickly access the network, right? So this is can be like saving some delay for the initial access. But actually, this is, you can say, it's kind of theoretical things, but I believe it will not be that noticeable whenever you configure it as a time point of view or as a point of view, because it's happening very fast at the end, especially for the C band or the small bands, which is maximum having 100 megahertz. This is, yeah, might be having an impact when you move to the midway. But the second part, it's very important. It's about the hosted downlink available response blocks. Actually, SSP can host location can host some of the available resource blocks. How this can be done? For example, assuming here the figure on the left. Here, this is assuming that the SSB was being configured in the center of the bandwidth and it was not aligned with the RBG allocation. As you know, the scheduling can be done through RBG. RBG, which is the resource block groups. For example, here assumed an example which is equal to 4 resource blocks. And as you can see here, for example, the SSP location started from RBG0, last RB. So as you know, that SSP consume usually 20 resource blocks, right? So this is 20 resource blocks. So it will keep moving. So now it will move till RBG5 here. So in this case, the SSP will reserve 6 RBG here from RBG0 till RBG5. This is in case if you configure in this way in the center of the bandwidth. So the SSP can reserve 6 resource blocks or 6 RBG and can in this case can host 4 resource blocks. And in case if you configure in the center of the bandwidth, it will only having 5 RBGA. So this means now you are having no hosted resource blocks. This can improve your maximum downlink speed as well. So this is also one of the consideration you need to really consider. But usually the operators have this part, or the vendors have this one being automatic configured. So this is I believe it's already being taken into consideration. The next part, it's about that, for example, assuming that you have 2 frequency bands, for example, same band, which is N78, for example, for site A, and C78 for site A for another site, for site B, for example. And both sites operating with the same exact same spectrum, especially for the first 60 megahertz, but one for 80 megahertz and one 60 megahertz. If you configure different speed location for different sites, first of all, this will cause, as you can see here, unnecessary interfrequency triggering. So because the handover is being done based on the SSP location, and also it can make some interference from SSP to the broadcaster channel. But in case if it's the same as here, as you can see in this figure, we changed the location for both of them will be fixed. So this will be interfrequency. So we are not going to interfrequency anymore. You can have SSP to SSP interference, but this is like it will be much better compared to SSP to broadcast channel. So this is also one of the consideration. The last part of today's session, it's about actually impact of the SSP on the uplink performance. Actually, this is you can consider as a rare case. This is related to the, as you know, we have a resource allocation for the BUCH resource allocation. It can be a resource allocation type 1 or type 0. Type 0 means the resource can be allocated non-contiguous or continuous or non-continuous, while resource allocation type 1 it require a continuous allocation of resource. And rarely when you find a device supporting only location allocation type 1 and not supporting type 0, for example. So how this can impact? First of all, you know that the initial bandwidth part, it's using the same location of the center of the SSP. For example, I'm speaking about the uplink. So what is the relation with this? The initial bandwidth part location will be based on the SSP location, because at the end it's frequency domain and DDD sharing the exact, for example, the downlink will be the exact same as uplink. So if the SSP is considered in the center of the bandwidth, this means the initial downlink bandwidth part will be in the center of the bandwidth, and the initial uplink bandwidth part will be in the center of the bandwidth. So assuming now you are configuring the center frequency here for the SSP at the center of the band, this means that your initial bandwidth part will be here. And as you know, the initial bandwidth part contains all the controlled signaling, even for uplink or downlink. So if you speak about uplink, you will have a BUCH, then BRAT here, then you will have a BUCH at the end. So in case of the device which supporting only resource allocation type 1, you will be able to take a continuous allocation or contiguous allocation. So you just cannot take this part, then take this part as well. You cannot. You can just need to take, for example, the last part, which is here from here. So this is non-continuous allocation for the resource blocks, and the device is not supporting to take both of them. So the GNB will only schedule this part. So in this case, the maximum speed for this particular user will be impacted. As you can see in this figure, for example, here in this figure, when the frequency range was at the center of the bandwidth, here the maximum, for example, getting RBs was 60 RBs, as an example. Now, in the case you move the SSP to the start of the band, so the initial bandwidth again will be shifted to the center of the bandwidth, and the BRAT will be allocated in the center of the bandwidth. So now the users can take more resource blocks. But this is in case we are only supporting resource allocation type 1. And as you can see in this comparison, for example, this particular device was only supporting uplink resource allocation type 1. So now the number of resource blocks being increased compared from the center to the start. And for sure, the uplink speed for a wireless 5G also increased from, as you can see, from the center to the start as well. And the last part here, this is actually usually, it's not very important, or I say that theoretically it's very important to understand it, but usually the vendors having a configuration where it's, especially in the initial configuration of the network, they consider the initial bandwidth part as a complete spectrum of the complete bandwidth. It's not like a small part, or it's not only, for example, if you have 100 megahertz, they will consider the initial bandwidth part as a complete 100 megahertz. So in this case, the BRATch will automatically move to the start of the bandwidth, the start of the initial bandwidth part. So in this case, you don't really need to require it by manual, in case if you have the vendors being supported this kind of feature. So actually, this is the last part of today's session. I hope if you like the content to share it and like with your friends, and we'll continue next sessions with the remaining parts of the NR planning. So thank you very much and see you next video.